My YouTube viewers, it's Crystal here. In this video, we're going to be talking about nonlinear regression, whereas the past two videos, we were talking about linear regression. The video before past was on simple linear regression, and the last video was on multiple regression, that's linear. So now what we're going to talk about is nonlinear regression. So nonlinear regression captures relationships that cannot be accurately modeled using a straight line, such as an exponential or polynomial relationships. The idea of nested models is essential for ANOVA model comparison, which we covered in the last video, I believe, likelihood ratio test, and principled model building. There are several types of nonlinear regression that can be utilized in R to include parametric nonlinear models, self-starting nonlinear models, polynomial regression, transformation models, spline regression, and LOES. So in order to demonstrate nonlinear regression, I'm going to cover two programs with nonlinear models. So the first program we're going to cover is nonlinear least squares, and that's the NLS function in R. So the first thing that you're going to do is you're going to set your seed. So every time you run the program, the variables are going to be initialized to the same values. So you type set.seed brackets 1, 2, 3, and you can put any number you want within the brackets. And then what we want to do is we want to simulate nonlinear data. So x, which is your independent variable, becomes SEQ. You're going to be creating a vector, bracket 0, 5, and length dot out equals 50. And y is your dependent variable, becomes 2 times exp, that's exponent, bracket 0.8 times x, plus R norm, that's a randomly sampled normal distribution of 50 samples and a standard deviation of 5. And then so what you're going to do is you're going to take these x and y variables and you're going to convert them to a data frame. And so my data becomes data.frame x, y. And then after we have done that, we're going to fit the nonlinear least squares model. So fit becomes NLS, that's nonlinear least squares, brackets y tilde a times exp, brackets b plus x, comma, data equals my data, and star equals list brackets a equals 1, b equals 0.5, and then we're going to fit, we're going to summarize the fit. So when we summarize the fit, your formula is y tilde a times exp, brackets b times x, and your parameters are your estimate, STD, your error, or your estimate, your standard error, your t value, which means that you ran this program up on a t distribution, and your p-value, and you're going to run that up on A and B. And so significant codes, it gives you these significant codes. Your residual standard error, that's RSS, is 4.678 on 48 degrees of freedom. And so you've got 50 samples, and then you've got 2 variables, so 50 minus 2 is 48. So the number of iterations to converge is 6, and the achieved convergence tolerance is a really low number. It's 8.333 to the negative 8. Okay, so now we're going to plot the data. So plot brackets my data $x, comma my data $y. PCH is the size of the dot, is 19. Color equals RGB, that's a vector to do with coloring. bracket 0, 0, 1, 0.5. Main is your title, which is nonlinear regression using NLS. XLab is your label on your x-axis is x, and YLab is your label on your y-axis is y. So we're going to add a fitted curve to that. So curve brackets predict, so we're making a prediction, brackets fit, comma, new data equals data.frame, brackets x equals x, add equals true, color equals red, line width equals 2. So we run it, and this is the chart that we've come up with, and it's a nonlinear regression using NLS, and NLS stands for nonlinear squares. And then so you can see that the curve that is made is nonlinear, and you can see that the dots on the chart that are made are nonlinear as well. So that's using the NLS function in R. So now what we're going to do is we're going to use polynomial regression. So we're going to set the seed. So every time you run the program, the variables are going to be initialized to the same value. So it's set.seed brackets 1, 2, 3. And so we're going to simulate nonlinear data. So x becomes SEQ, that's sequence, bracket 0, 10, length out equals 100, and y becomes 3 plus 2 times x minus 0.3 times x squared plus r norm brackets 100 with standard deviation of 3. So r norm is a randomly sampled normal distribution of 100 samples and a standard deviation of 3. So we're going to take the x and the y variable, and we're going to convert it to a data frame. So my data becomes data.frame brackets x.y. And now we're going to fit the polynomial regression. So model becomes LM, that's your linear model, brackets y tilde poly brackets x, 2, data equals my data. And then we're going to summarize the model. So we're going to call the formula LM is linear model, brackets formula equals y tilde poly brackets x, 2, data equals my data. And you've got your residuals of your minimum value, your first quartile, your median value, your third quartile, and your maximum value. Then you've got your coefficients for poly, for your intercept, and poly x, 2, 1, and poly x, 2, 2. You've got your significant codes, and you've got your residual standard error is 2.743 on 97 degrees of freedom. So you've got 100 minus 3 is your 97 degrees of freedom. So you've got your multiple r squared is 0.6071. Your adjusted r squared is 0.599. Your F statistic is 74.95. And on 2 and 97 degrees of freedom, your p-value is really low, being 2.2 e to the negative 16. So now we're going to plot the data and the fitted curve. So plot brackets my data $x, my data $y, PCH is the size of the dot, it's 19. Color is RGB, and that's a RGB code for dealing with color. It's bracket 0, 0, 1, 0.4. Main is the main the title is Polynomial Regression of Quadratic. XLab is the label of the x-axis, and YLab is the label of the y-axis. So XLab is x and YLab is y. And then we're going to generate a smooth curve. So x new becomes SEQ, that's making a vector, brackets min x, comma, max x, comma, length out equals 200. And ypred, that's your prediction, becomes predict, brackets, model, comma, new data equals data.frame, bracket x equals x new. You're going to put some lines in there. Lines, brackets, x new, comma, ypred, comma, color equals red, line width equals 2. And then so you've got x and a y variable, but you've got like, and then so we're going to run it. And this is the chart that's made. It's a polynomial regression using a quadratic formula, and you can see that the line that is made is definitely not linear. So this is a polynomial regression. And so that's going to complete this video. If you do a search on R, you'll find out that there are many nonlinear regressions that you can perform using R, but I just decided to use the polynomial regression and the nonlinear squares regression, but that's not the only one that you can use. That's just what I decided to use in this video, but if you do your research, and you will find that there are several nonlinear regressions that you can perform in R. So that concludes this video. The next video is going to be another statistical topic, and I hope that you decide to watch the next video, and I hope you got some valuable information off of this video.